In this video, I'll be talking about dual of a primal. So let's see what is dual and what is primal. So suppose that we have been given a linear programming problem, and this given linear programming problem, we'll call this as primal. Corresponding to this linear programming problem which is given to us, we have called this as primal, we have a dual. And this is also a linear programming problem which we have obtained from the given linear programming problem. And since both of them are linear programming problem, and just to differentiate these two, one problem we have called it as a primal and another problem we have called it as a dual. Now the question is how to write this dual from the given linear programming problem. So this is my first question. And the second question is, what is the relation between a dual and a primal? And why do we need this dual from this primal? Because both of them are actually going to look like a linear programming problem only. And as far as the solution is concerned, we have already seen in my previous video that whatever a linear programming is of the type, say for example, you have either objective function as maximum or objective function is minimization. We have this z is equal to c transpose x which we want to optimize, and you may have any type of the constraint where either you may have less than, greater than or equal to, and even your decision variable may be either unrestricted in sign or maybe they are non-negative decision variable. We can already solve this linear programming problem. Then why do we require this dual? So we will study this also. What is the relation between a dual and a primal? And my third question would be, what is the economic interpretation of a dual? And here we'll study the dual is called a shadow price, or dual is called as the unit worth of resource. So we know that whenever we are constructing a linear programming problem, it is important that we construct the linear programming problem by understanding what is the resource available, or we say what is the demand corresponding to them. So for the resource, we always say that whatever is on the left hand side, which we get it either by involving decision variable, we say let's say 50 unit of the resources available corresponding to the decision variables, whatever we'll use here. Say for example, we have x1 plus 2, x2, and these are some unit corresponding to some component that we are trying to create in a particular problem. And so it depends upon what is a worth unit of your resource. This has some connection with the dual. So that is why we call this as unit worth of resource or the shadow price, and that's how we define the economic interpretation. Now the second and the third part I'll be covering in my next video. Let's start in this particular video how to write the dual of a given primal. Now before I actually write the dual of a primal, let me to just give you an understanding way of about dual and primal. Let's consider a matrix, and I'm here considering an example. Suppose this is a matrix of order 2 cross 3. Corresponding to any matrix we write of any order, we can always write its corresponding transpose. And for the transpose, what rule do we apply? Write each row as a column, or maybe write each column as a row. So now I get 2 1, 3 2, 4 7, and so the order which we have written here earlier 2 cross 3, now this become 2 cross 3 cross 2. Or we may say that if A is a matrix of Aij element and here the order is m cross n, then A transpose is a matrix of the order n cross m. And also notice that whenever we take the transpose, so this will give me the same again transformation, and I get back m cross n, which is my original matrix A. Now this is what is happening in dual also. So for example, I have the primal linear programming problem, and corresponding to this I have written a dual, and dual is also a linear programming problem. Now assume that this is your initial problem. So when you will find dual of this particular problem, so it becomes dual of dual, okay, which is a linear programming problem. So here I should get back my primal problem. So this is something what is happening in the transportation also. Now of course the rules are a little different. Here it's only with respect to a matrix, and I could have write it as transpose. But let's say what is the rule for writing the dual of a primal. Rules for constructing the dual problem is that first write the LPP, which is our primal LPP, write primal into standard form. So once we write this LPP into standard form, we know that the constraints are coming with the equality, decision variables are non-negative, and the right hand side is also non-negative. So this is kind of a prerequisite condition. So let me to mention here prerequisite condition. Now we can define the rule for the dual. And so let us write here standard primal form. So this is standard primal problem. And then I'm going to write the dual. Again, in the primal problem, we have two type of the objective function. Either we can have maximization or we can have minimization. So let us first consider that if we have a maximization problem. So maximum z equal to c1 x1 plus so on up till cn xn. These are the objective function. This is the objective function subject to the constraint. Now let me write the constraint into the matrix format. So this is the coefficient matrix, decision variable, and here we have already converted this into equality right hand side, and x greater than or equal to 0 non-negative. Now A was a matrix which A is a coefficient matrix, and this coefficient matrix has Aij as elements with the order m cross n. That means there are m number of constraint and n number of decision variable. And this B is column vector. So for the column vector, maybe I can just simply write this as B1 up till Bm. There were m number of constraint. So put this as transpose. Now corresponding to this standard form, I will have the dual problem as objective function will become minimization of z star. And now let's define this B. This goes into now objective function since it represents a column vector. So we have to now keep it as B1 y1 plus B2 y2 plus so on up till Bm ym. From here we can see that there are m number of new dual variables I have defined. So dual variables count is equal to the count of the constraint written in the primal problem subject to. Now here we got A. So right here in the dual problem, write A transpose multiply by new decision variable, where I am just writing capital Y as the column vector y1 up till ym. So these are my decision variable in the dual problem. And if it is minimization, I have to keep a sign on the constraint as greater than always. And here you get C transpose. C transpose is this row vector which is now turning into the column. And here Y decision variable are unrestricted in sign. So this is the definition for writing the dual. So that means whenever we convert the LPP of this sort, if it has the objective function as maximization, it will convert into minimization, and the constraint will always be greater than, and the decision variable will always be unrestricted in sign. Now suppose that if you have the standard primal problem with the minimization objective function, so we can also have, and if this problem is minimization, again with the same thing, so I can write this as now combinedly C transpose x subject to Ax equal to B, x greater than 0. So if this is the primal problem, corresponding to this we will now write the dual problem. And for the dual problem, objective function was minimization, so here it will become maximization z star. The right hand size B will go now into the objective function, so this is B transpose Y subject to, instead of A, now we have A transpose capital Y. This is less than or equal to C transpose will become C only, and Y is unrestricted in sign. So this is the decision variable which are unrestricted in sign, and that's it. This is what we call it as dual problem. Now with this definition, there are few certain rules which are very obvious that I'm now listing. So we have, for every primal constraint there is a dual variable, and for every primal variable there is a dual constraint. So this I have written again in the D point. Number of dual constraint is equal to number of primal variables, and number of dual variable is equal to number of primal constraint. And the third was the coefficient of dual variable in the constraint are same as the coefficient of primal variable. So this is about A matrix in the primal problem, and then in the dual we have A transpose matrix. So the coefficients are essentially the same, except then they are being transposed. And the last one, the objective coefficient of the primal variables. So the objective coefficient means cost will become the right hand side constants of the dual constraint, and the right hand side of the dual constraint becomes the objective coefficient of the primal problem. So I can again summarize this information in a table, and let's call this as standard primal objective. If the standard primal objective is, here we have a maximization problem in the primal, and remember that we have converted the LPP into standard form, and another possibility could be that if the objective function is a minimization problem. So, and we have already written, so writing primal in standard form. So the standard form I have already discussed in my earlier video also. So basically it is optimization Z equal to C transpose X. The constraints are written with equality involving slack surplus variable and decision variable are non-negative. So if this is the standard primal objective where the primal is in the standard form, the dual corresponding to this will become, here let's talk about how objective function will write. Objective function will become maximization. So it will give me a minimization. It will give me a opposite one. If it is minimization, this will give me a maximization. Constraints will become greater than, in this case with the minimization I will always have a greater than constraint. With maximization I will have a constraint less than type. And the decision variable are unrestricted in sign in both the cases. So if we have the equality constraint here, basically the constraint correspond to the decision variable. If you have an equality constraint, you will have an unrestricted decision variable in the dual problem. And now let's do an example. Here I want to write the dual of the given primal, and notice that the primal is maximization. So the first thing I need to do is to write the dual, is to write primal into standard form. So write primal into standard form. So once you write the primal into standard form, the constraint will appear with the equality sign and the decision variable are non-negative. So this will become maximum of Z equal to 5x1 plus 12x2 plus 4x3 subject to x1 plus 2x2 plus x3, and this is less than, so I need to add a slack variable equal to 10. Second constraint is already in equality, so we do not need to add anything. We will keep this as it is. So we have x1, x2, x3 and s1 greater than or equal to 0. Now this is of the desired format. We have just done, if this is maximization, in the dual I will have a minimization, and minimization will come with the sign greater than. So now let's write down the dual corresponding to this. So for dual, the first thing I have to fix the objective function. Minimization of Z star equal to, how many new decision variable I need to introduce? We introduce two decision variable y1 and y2 depending upon the number of constraints. So I have told you the decision variable count is equal to the constraint in the primal problem. So the right hand side goes into the objective function. This is the right hand side of the primal which will go in the objective function. So this is 10 into y1. So basically this was b1 into y1 plus 8 into y2, that is plus b2 into y2. And the cost will come as the right hand side constant. So subject to. Now you also notice that here the coefficient matrix capital A is 1, 2, 2, minus 1, 1, 3, 1, 0. This is corresponding to x1, x2, x3 and s1. So if I find the A transpose corresponding to this one, it will give me 1, 2, 2 minus 1, 1, 3, 1, 0. And I need to now multiply A transpose Y, since this is minimization. So put this as greater than or equal to C, the cost coefficient which appear here. And of course you can add a 0 times S1 cost because of the last decision variable. So if I just keep this B as 1, 2, 2 minus 1, 1, 3, 1, 0 with two decision variables that we have newly introduced, greater than or equal to, this is the cost vector 5, 12, 4, 0. So when I multiply, I will get the constraint. This is y1 plus 2y2 greater than or equal to 5, 2y1 minus y2 greater than or equal to 12, y1 plus 3y2 greater than or equal to 4, and y1 greater than or equal to 0, because it is 1 into y1 plus 0 into y2 which is greater than or equal to 0. And we have also said that the y1 is unrestricted, the decision variable are unrestricted, and y2 is also unrestricted in sign. But now you can also see that in my previous condition we have already mentioned that y1 is greater than or equal to 0. So this unrestricted, basically then we need to find the intersection of these two. So here we will replace this condition simply by mentioning that y1 is greater than or equal to 0 and y2 is unrestricted. So this becomes a dual of the given primal problem. Now let's take another example, and here also I want to write the dual of the given primal problem. And for this again, let me to write the primal problem again with equality constraint. So this will become minimization of Z equal to 15x1 plus 12x2 subject to the constraint x1 plus 2x2, and you can see that this is greater than first constraint, so I will have minus s1 equal to 3, and the second is 2x1 minus 4x2. Now this constraint is less than, so I will have a slack variable which is plus s2 equal to 5, and then we can have 0 into s1 plus 0 into s2. And decision variables, these are non-negative decision variables. Now the first thing that I need to look at here in this problem is, this is a minimization and constraints are all equal. So now I can write the dual corresponding to this. If this is minimization in the dual, I should have a maximization by rule, and let me to define this as W. General formula for the primal was minimization of Z. You have some C transpose X, AX equal to B, X greater than or equal to 0. Corresponding to this, we will have the dual where we'll have a maximization of W equal to this. Right hand side will come in the objective function B transpose Y, and here you will have A transpose Y less than or equal to C transpose will become C, and Y is unrestricted in sign. So this is what we have done. Let's see again. Maximum of W, and again you have two constraints, so put y1, y2. Now look at only the coefficient of x1, which is now in a column, will go in a row with respect to these variables. So here you will have y1 plus 2y2, and then so on this side we'll have less than or equal to 15. As you see that with maximization we'll have to put less than sign. With minimization we were having greater than sign. And then look at the second decision variable. So this will give me 2y1 minus 4y2. So basically I am multiplying A transpose with y less than or equal to 12. 15 is this, 12 is this. Then you got minus y1. Notice as s1 is appearing in the first constraint, it is not appearing in the second constraint. So this is 0 into y2 less than or equal to 0. And then similarly s2 is appearing in the second constraint, but it is not appearing in the first constraint. So this is 0 into y1 plus y2 less than or equal to 0, and y1, y2 currently they are unrestricted in sign as per the rule. But we'll see again with respect to these one. And in the objective function we got 3 into y1 plus 5 into y2. So this is 3 into y1 plus 5 y2. Now let's see all together again. And here minus y1 is less than or equal to 0, and here y2 is less than or equal to 0. So now from these two, and also noticing these two, because I need to find the range which I need to find a solution which satisfy all the constraints. So from these two we can directly say that y1 is greater than or equal to 0, because minus y1 less than or equal to 0, so y1 is greater than or equal to 0, and the second will give me y2 is always less than or equal to 0. So basically intersection of these two conditions, and hence this becomes the dual of our linear programming problem or the given primal. Now let's take one more example, and here I have a maximization problem whose dual I want to write. Now this you can see that here some of the constraints are equality, some are greater than, some are less than, and x1 is unrestricted in sign. So this also I need to convert into non-negative decision variable. So writing this LPP into standard form, what I will get here this problem as, so primal is, this will become first maximization z equal to 5, and since x1 is unrestricted, so unrestricted decision variable we can write it as subtraction of two non-negative decision variables. We did this in my earlier video also. So write any unrestricted decision variable as a subtraction of two non-negative decision variable, and then do the replacement. So this will become 5 times x1 dash minus 5 times x2 double dash plus 6x2, and then let's say the constraint will become x1 dash minus x2 double dash plus 2x2 equal to 5. Second constraint will become minus x1 dash plus x2 double dash plus 5x2, and the constraint is also greater than. So let's add a let's have a surplus variable also, s1 equal to 3. So this is minus s1, and then we got 4x1 dash minus 4x2 double dash plus 7x2, and then have a slack variable s2 equal to 8. So now all the decision variable are greater than s1, s2 greater than or equal to 0. Now the LPP into standard form, and we can immediately write the dual of this primal problem. So for the dual, As we observe that objective function is maximization, so here we will have a minimization and W. How many decision variable we need to involve in the dual problem? We got y1, y2, y3. As we got 3 constraint in the primal problem, so we need to have 3 decision variables in the dual problem. So we will have 5 times y1 plus 3 times y2 plus 8 times y3. So this is simply 5 times y1, 3 times y2 and 8 times y3 subject to the constraint. Now look at again, as I've already told you, corresponding to this we have the matrix A, and corresponding to this we'll have the matrix A transpose. So that means its column will become the row in the dual. Look at the column of one particular decision variable x1 dash, which will become a row with these decision variable. So here the first row will become, look at the coefficient of x1, this is 1 into y1, and then get minus 1 into y2, and then we got 4 into y3. So I will have my first constraint as y1 minus y2 plus 4 times y3, and this is minimization, so the constraint greater than, and we'll have this 5 cost will come here. Then the second constraint, look at the coefficient of only x2 double dash. So we will have minus y1 plus y2 minus 4y3 greater than or equal to the second cost minus 5. Then look at the decision variable x2, and so it will give me 2y1 plus 5y2 plus 7 times y3. This is greater than or equal to 6. And as we notice that 0 into s1 plus 0 into s2. So the other constraint which is corresponding to s1 and s2. So there will be 2 more columns here, and 0 into y1 minus y2 plus 0 into y3. This is greater than or equal to 0, and corresponding to the last constraint we will have 0 y1 plus 0 y2 plus 1 into y3. This is greater than or equal to 0. And now look at the decision variables. So decision variable y1, y2, y3, they are unrestricted in sign as we have decided in the table 1. Now again notice that because of these two, so this will give me minus y2 greater than or equal to 0. So this gives me y2 less than or equal to 0. And this gives me y3 greater than or equal to 0. So this condition together with these conditions, we can have dual as this, and where I have y1 unrestricted and y2 less than or equal to 0, y3 greater than or equal to 0. In fact, we can look at the first and second constraint again. First and second constraint are exactly same, they are negative of each other. So if I look this particular constraint and I multiply both sides by a minus sign, so what I will get this constraint as y1 minus y2 plus 4 times y3 less than or equal to 5. Now notice that first constraint, this constraint and this constraint, if they are taken together, because now they are appearing together, so from the first and second constraint I can rewrite my dual as this, and here you can notice that the first constraint appears equality. So now there are not 3 constraints, there are only 2 constraints in the dual, because I have written the first and second constraint together, and that makes an equality constraint. These decision variable I have already explained. And so we can have this as a dual corresponding to our primal problem. Now also notice that for writing the dual corresponding to this particular primal, we have followed certain steps. We have written primal into standard form, and then from the standard form we are trying to write the dual as defined in the, and then we have finally reached to this particular format. But now I will give you a table 2 where we can directly write this dual from the primal in one step, just by noticing what is the objective function, what are in the constraint, and how many constraints are appearing and how many decision variables are appearing. I will explain in my next video.